Hello all, in this video we will learn about fine-tuning large language models. This is a part 1 video, so we will understand the fundamentals of fine-tuning, the differences between the prompt engineering, few-shot learning and fine-tuning, the possible task, that is the applications of the downstream task that we call as, and the domains we can focus while fine-tuning, how to create a data set for fine-tuning, the parameters that we need to consider while fine-tuning a large language model, a simple Python code to understand the usage of these parameters, and finally, we will understand how to fine-tune a BERT large language model using a BioASQ benchmark dataset for question answering task. So this BioASQ benchmark dataset is a biomedical domain dataset extracted from PubMed articles. So maybe in this part 2 videos, we will understand about the types of fine tuning, and it is advisable to learn about the fundamentals of large language model before understanding the fine tuning of large language models. Okay, so now we will understand what is fine tuning. So in the earlier video, we saw that a base model, so that is a large language model, is primarily a language expert. So when we fine tune, the language expert becomes a domain specific expert to do a particular task. That's how we should understand, we can understand fine tune, right? For instance, like the task can be like, as we saw earlier, like the task can be a machine translation, it can be a chatbot, it can be a speech recognition, it can be any task. So but while doing that task, we are also making the large language model to be a domain expert. So that's what the fine tuning does to an LLM. So we'll understand through this picture. So we have a base model. So this base model is already built by large enterprises. It can be GPT 3.5 or Llama or Mistral. So when we ask this particular query to this large language model, it might not answer properly. Why? Because it might not be an expert in that particular domain. So in that case, what we can do is that we can supply a small amount of data pertaining to the domain and we can make it work. So this is what we call it as a fine tuning. So what we are doing is that like we're improving the performance to do a particular task on a particular domain use cases, we can call it as. So that is fine tuning. So we will understand through an example. So let's say we are giving a query like this. So summarize this patient note for a referral letter. A referral letter is usually given by a medical practitioner to another medical practitioner. So the before fine tuning, the large language model gives a very generic answer. So without any technical jargons, you can understand, you can see, observe that there is no technical terms. Why? Because the particular large language model is not aware of those technical terms. So that is the reason. So after fine tuning with clinical notes, then it will have the technical details and it will elaborately answer the query. So that's what fine tuning does to a large language model. So fine tuning is primarily making it to be making it a domain expert. Plus, we are increasing the precision and clarity in the answer. Why? Because it knows the domain, so it is able to answer very well. So that's what it means. Okay, now as I said earlier, fine tuning is all about making a large language model as a domain expert to do a particular task. We will understand. So there can be a number of domains. I thought of listing these 4 domains, that is healthcare. So maybe in healthcare, so we can think about a task like fine tuning to convert a messy handwritten clinical notes into a structured EMR ready summary for doctors. So handwritten notes versus like EMR. EMR is electronic medical record. So we are digitalizing the clinical notes. So we can train an LLM to do this. So primarily this task is nothing but like creating summaries, but the domain is healthcare domain. So when you talk of e-commerce, like e-commerce, where we have like Amazon, so we have products and we can generate multilingual product descriptions based upon the region in which the e-commerce product is sold. So this can increase the SEO. So here the task is multilingual product description. So generating product description is the task and the domain here is the e-commerce domain. So in customer support, we can create a chatbot that can actually help the customers to ask about a particular brand using from the manuals. So we can train the manuals and we can fine tune the large language model with the manuals so that and we can build a chatbot. So the task is the chatbot, but the domain is the customer support. So similarly, we can also do it for HR, wherein we can fine tune the large language model to extract the resume. So extracting resume is the task here, and the domain is the HR. So likewise, like we can think of a number of tasks and we can do it for a number of domains. That's what I wanted to convey here. Okay, so now, so this is how we create a data set for fine tuning. So this is an example for fine tuning data set for clinical note summarization. This is how the data set will look like. We will have a set of prompts and its corresponding responses. The prompt is basically a medical practitioner would give in the LLM. So this is the prompt and this is the expected response. So we need to prepare a set of prompts and responses, and we need to teach it to the LLM. So that's what we need to do. Okay, so now we'll understand when to fine tune. Okay, so before we understand when to fine tune, we should understand when not to fine tune. So we need to understand, like we need to know, because fine tuning is a very costly process. So we cannot always fine tune, or we need not always fine tune. Why? Because when a particular LLM is already an expert in that domain, we don't need to fine tune. It's enough to do a prompt engineering by giving one or few short inferences. What it means is that, so let's say here the task is whenever we give a review, that particular LLM is supposed to give the sentiment of the review. So it's supposed to give it as a positive or a negative. So this is the task we are expecting out of the LLM. So for this, we can just give few examples. That's what it means here. So one or few short inferences. So we give the review, we are just giving the prompt, classify this review, we are giving the review, and we are giving the label sentiment as positive. So this is one shot actually, but if it is not able to answer, you can have few more shots so that it is able to pick up the task. So then if we give the review in the same format, it should be able to label it as a positive or negative depending upon what was the review given. So this is about like prompt engineering or through a few short inferences. Okay, so the primary difference between prompt engineering and fine tuning is that, like, we do prompt engineering by tweaking the prompts, because like sometimes LLM may not be able to answer. Why? Because like the prompts are not proper, so that it is not able to capture the context better. So but it's a domain expert in that particular domain, so it is enough to only tweak the prompt. So that is prompt engineering. But if that LLM is not an expert in that particular domain, so be it healthcare or HR or whatever, so then we need to supply the domain specific details. So that's a primary difference, but these are the like other differences we need to consider. Like, yeah, so prompt engineering, it's like through definition we are tweaking the prompts, and fine tuning is like we're training the model. So that's a costly process, training a model by preparing a new set of data. So an effort is like, obviously it is quick. So we need to only tweak the prompts. So it is not going to take much of efforts, but fine tuning is not so. We need to create the data, and then we need to create the training. We need to do the training of the model, so which needs computational power. So when to use, like occasionally when task specific outputs are needed, like if we use ChatGPT, we normally ask questions, but sometimes we need ChatGPT to do a particular task. Occasionally only we do so. So for those purpose, like we can use prompt engineering. But fine tuning is when like you are requiring a domain specific expert for a domain specific, for a domain specific task. So a medical chatbot or a medical summarizer. So consistently, that is what is needed. It is not occasionally asked. So in that case, like we need to take up the step of like fine tuning. So flexibility, it is easy to change anytime. Like once you you do that task, and next time, like you can just come out of the task and make it. As use as a as we do Chat GPT. So we don't need to always do that sentiment analysis like we saw in the earlier example. So we don't need the same task again and again. So we can shift the task. So but once fine tuning is done, it remains as a domain expert. So it is rigid. So cost, of course, this is free. So because we don't have any, of course, if it is a paid LLM, we are doing this prompt engineering through paid LLMs. So then there is a cost involved, but it is minimal. So this prompt engineering is not going to incur any extra cost. That's what I'm trying to convey here. But fine tuning, as I said earlier, like you need data preparation that involves manpower, and we need to spend for that, and computational power as well. So I just thought this is an example to just show the differences between prompt engineering and fine tuning. So summarize the clinical note in professional medical language. So this is the prompt given. So we can check the model before going to fine tuning, and by tweaking the tweets, if it is not tweaking the prompts, I'm sorry. So to check whether it is already a domain expert, we can tweak the prompts and see if it is able to answer. That's what is prompt engineering. Fine tuning, we need to prepare the prompt and responses as we saw earlier in sample data set, and then we need to change the model weights, and then we need to train the model. So that is fine tuning. So just to show how the model will respond before fine tuning and after fine tuning. So it gives a very short answer, like very shy answer, but it becomes talkative after it is fine tuned because it knows now more details. So it is able to confidently answer, give more details about the query. So that's how a fine tuned model will behave. Okay, so this is about the key hyperparameters which we need to consider while we do the fine tuning. So I'm talking about the implementation perspective. So when you start the fine tuning, so we need to consider these parameters. We need to tweak the values of these parameters, and then we need to go for fine tuning. Learning rate, like as we already know, like these are the a large number of step or the tiny step a model can, how faster or slower a model can actually learn the weights during the training process. That is learning rate. So the lower is the learning rate, it is actually good. So batch size is nothing but like the entire prompt and response data set we have. We are not going to pass all the prompts and responses in one go. So we will put it in multiple batches. That's what batch sizes mean. So it's often between these two these numbers. And number of epoch. Epoch is nothing but like we have a data set. So the number of epoch is nothing but like the entire data set is how many times it is passed through the model once. So that is epoch. So how to understand this? Like an epoch will have number of batches. Yeah, so gradient accumulation is done like to avoid frequent update of weights. So when we use multiple batches, so the model tends to update its weights. So that the I mean and then we have a stringent hardware, so we cannot afford to have the updating the weights frequently. So we will have gradient accumulation. That means like we will not frequently update. So that's how we should understand this. And weight decay. So it's a regular L2 regularization. So that means like regularization techniques penalize large weights in the model to prevent overfitting. So overfitting is nothing but like the model behaves well during the training, and during testing it poorly performs. So the features are given less weightage. So to avoid overfitting, we do this weight decay. Learning rate scheduler. So we keep on, we don't have a one learning rate throughout the training process. We dynamically change it during the initial warm up or decay. So like during the warm up, initial phase of training. So that is warm up. So we will keep changing this like through the learning rate scheduler. Dropout is again a regularization parameter. So like certain neurons are prevented to prevent overfitting. So we drop out certain neurons to zero. So that the overfitting is prevented. So this is again a regularization technique. So attention heads. So I think the earlier video we talked about multi-attention heads. So we learned that like BERT has 12 attention heads. So this can be reduced if you have a stringent computational power. I think sometimes the particular language model will have a fixed attention heads. So that we need to check. And maximum sequence length. So maximum sequence length is the number of tokens that a model is trained with. So it is 512 tokens. So the larger is the the sequence length, so the larger context it can actually handle. So optimizer is ladder optimizer, like this is an optimizing function, so that controls the loss. Yeah, so this is a summary of hyperparameters. We just need to we don't need to understand about each and every learning parameter, but in detail. But we need to understand, what we need to understand is that, like, what is the value that is normally used for each and every parameter that we need to check out. So these values are what are the optimal values that are used for each and every model. So that knowledge we have, so that our fine tuning goes easy. So, and yeah, so one more thing. So these models are million parameter models. We can see that the batch sizes are higher. So that means for these models we are giving multiple batches. The input is not passed in one go. And we can also see that, like, the epochs are same for both the million parameter model and the billion parameter model. But we can see the differences in max sequence length. So these models are only able to take up 128 or 256 sequence token, that is the number of tokens at a time. But we can see these million parameter models are able to digest 512 tokens at a time. So they have a higher context understanding capability. So gradient clipping is again to just avoid the gradient exploration. So to just have a decreased value, so this gradient clipping is done. The gradient is related to the updating of weights. So you just need to know the optimal value that is used for each and every model. Then you can tweak the value accordingly in your code. So we'll see a sample code to understand how these um, parameters are used in the model. So the format of the code is very simple. So initially we will have all the libraries imported, and yeah, so you don't need to worry about this weights and biases. I've disabled this environment. And the model, so initially we will have the libraries installed, and I have used only million parameter models here to just keep it very simple. So bird based uncase is the model I've used. So to just to showcase how these parameters are used. So I've given only two data sets. So we don't need to fine tune here. So, but just to showcase how the parameters are used in the code. So I've just given only a toy data set, but in reality, it will be with a more prompts and response. So the task we are focusing here is the sentiment analysis. For I love programming is given label 1. I hate bugs is sentiment, negative sentiment, that is 0. So 1 indicates positive and 0 indicates negative. So we have given the data set, and we have loaded the base model. So base model is given. Now the data set is given. Next, the parameter. So the parameters, so as we saw earlier, so the values of the parameter is checked. So if you have a stringent computational resources, then you can see tweaking these parameters as per the advisable values, and then you can run your code. So yeah, so and then finally after the fine tuning is done, so finally you will see the fine tuned model saving in your drive. So this is the format. So then you can give to the fine tuned model, you can give an test input and see the prediction. So the format is like, we will have the libraries installed, you give the data, load the base model, set the parameters, and we save the pre-trained, do the fine tuning, save the pre-trained model, and then we can give the testing. So this is the format of the code usually that you can see in the fine tuning codes. So here to this fine tuned model, I'm giving I enjoy coding. So I've already run this code to save time. So it is giving the predicted label 1. So that means it is positive. So this is about the code, like to show how these parameters are used in the code. So in the other code, we will see how we can fine tune for the domain, I mean biomedical domain. So this is about fine tuning BERT for the biomedical domain, and doing the task of like question answering. So the task is question answering, and the domain is biomedical domain. So this is the BioASQ factoid data set. So I've already uploaded this dataset. You can upload it here or you can put it in the drive. So when you upload it here, and you can copy path, and that's how I got this path. So if you put it here, like when you close this code, like this goes away. So every time you'll have to upload this file. So the other way to do this is like you can put it in the drive and you can mount the drive. So there are two ways of using it. Okay, so we have loaded the data set, and I'll just show the format again. So just to register that in your mind. So format, uploading the data, and loading the model. So the model is again BERT. Yeah, so we have BERT base uncased, loading the model, and uh, this is parameter. So we are setting the parameter again. So you see the parameters, and then we are training it. So after training, so the fine-tuned model will be saved here. So to this fine-tuned model, we can ask a question. So here I've asked the question. So after this is, you see this when the fine-tuning is happening. So you see this like epoch. So I've set the epoch 3. So you see the loss getting reduced after each and every epoch. If you would have run more epoch, then it would have got better. So, but for simplicity, I've just kept 3 epochs. So accuracy, precision, and recall and F1 scores are calculated. So these are not so good. So you can make it better if you have if you go for more epochs. Yeah. So to the saved model, finally we are saving the model. So we are asking a question. So what are the symptoms of COVID-19? So a predicted answer is given. So that is the format of the code. So once again, I'll say the format, like we need to load the data, and then data, and then the model. So these are what you see, these lines are like data pre-processing lines, and then you need to load the model, and then we have to set the tokenizer, and then we need to set the parameters, and then do the fine tuning, save the model, and to the saved model we will ask questions. So now I'll just have a look at how this, we'll see a look at like how the data will look like. This is how the BioASQ data will look like. So it will have a question and it will have a context. So the context is the question answering data set format is like this only. So it will have a question, and from this context it will pick up the answer. So that's how you can think about question answering. Question answering is about like you have a document and you want to pick up an answer from that particular document. So you're basically questioning the document. So the document is the context. So since we have used only BERT, the context is very less. So but when you use larger models, like you can have document itself. So this is how this is a benchmark data set, and this format is like this. So they've given the JSON format. So a question is given and a context is given. So the text is like prompting. This is I mean, this is the possible answer, and it starts from the 31 character. So the 31st character, like the answer is starting. So this is how the data set starts. This is how the data set looks like. So hope you got a feel of like what is fine tuning. So using these codes. So in the next video, we will understand the types of fine tuning and how to efficiently do it using PEFT, LoRa, and QLoRa methods. So thank you for watching.